It's my pleasure today to start the Informal Systems Seminar with a presentation a presentation by Emanuel Rapsch, excuse me, Emanuel Rapsch, who's a researcher at the Stochastic und Finanzmathematik group team at the Technische Universität Berlin. Emanuel, correct me if I'm wrong, but we first met at the Berlin meeting. Was that in 2022?
Yes,
Is
that's
that
correct.
Yes, that's right. When he gave a fascinating talk there, which was, I believe, in late mid-path of his dissertation preparation. Again, I'll ask him for corrections. And now he's completed his dissertation and is a member of the faculty which I've just listed at TUB. So that he's previously studied at Oxford, Berlin, Lyon, and at Freiburg, and has an MSc in mathematics from Lyon. Okay, as you'll see, his research spans game and decision theory and stochastic control, finance, mathematics, and environmental economics. Okay, so without further ado, and with apologies for the technical delay, I'll give the floor to Emanuel. And so let me just rearrange the screen here so that everyone can see what's going on. Okay, so okay. And this is I should emphasize that this is indeed a world distributed seminar. And in fact, we have participants from not only around Montreal and Canada, but also from the Cameroon, Africa. So please go ahead. The title is on the foundations of dynamic games and probability decision making extensive form. Emanuel.
Thank you very much for this very kind introduction. It's my most pleasure to give this talk today at Gerard. I remember very well when we met 3 years ago in Berlin. It was a very interesting discussion that we had, and actually, I had just started thinking about the um, the structures of the project that I'm now going to talk about to you. So I've seen on the internet that GERAD means Groupe d'études et de recherche en analyse des décisions. And I think this fits very well because of the following. My project is actually born out of control theoretic, financial economic applications on the one hand, and on the other, the conviction that thinking about decision making fundamentally in abstract terms, aiming at foundational theory, is a highly relevant endeavor. For without the proper understanding of what is a decision actually, what does it mean to calculate optimal controls and to infer advice on optimal decisions? What is an equilibrium? What is a counterfactual if we have no proper decision theoretic underpinning? So I ask these questions in abstracto, knowing that all this applies to a vast class of practical questions ultimately. More practically, I will be speaking about my doctoral dissertation, which I defended this year. In this text, I propose a foundational theory of dynamic games under probabilistic uncertainty, inspired by classical extensive form theory on the one hand, basic theory in game theory, and stochastic analysis on the other hand. My talk is structured as follows. I first give an overview on the general research question, starting from the idea that game theory is a language. Then I continue with a more technical introduction to the specific problems to be addressed and argue why we need an abstract, graded language of dynamic games and probability. So emphasis put on abstract and on graded. Then in the third section, I present the core notions of the strict reading of that language, which is covered in chapters 1 and 2 of my dissertation. And in the fourth and final and main section, I discuss a relaxed reading of this language. So it's somehow the grade 2, which applies to continuous time problems in particular. Okay, so these terms will become clearer, I hope, during the presentation. So let's just jump into the first section, Game Theory as a Language, following a motto by Goethe, doch ein Begriff muss bei dem Worte sein, so, but a concept must be connected with the word. Yeah, well, when consulting the literature and the social sciences in engineering and mathematics, it is not hard to find game-theoretic terminology, games, strategies, equilibrium, also types, signals, subgames, among many others. But the formal meaning often depends strongly on context and formulation. So, what is the conceptual meaning then? And is it more than discretionary, metaphorical thinking that motivates this coincidental use of words? So, do we assist a quasi-Babylonian confusion of tongues? Do we have a lot of different languages that cannot speak to each other? Or is it possible to find a translation device, a kind of abstract language that allows for comparison? So this project is based on the idea that when using game-theoretic words, they shall have a meaning in terms of first principles from decision theory. And in case of complex dynamics and complex uncertainty, this is not so clear. And thus, I propose an abstract language for formally comparing usages and meanings. And to start with these first principles, this is a quite general introduction, I'd say. Let me emphasize the principle of rationality, a very, very old principle in at least Western philosophy, which has a very particular meaning, but which is as old as controversial. And much of the critique of this principle is probably also linked to a kind of conceptual overstretch. So this is why I would like to emphasize a very specific reading of this. So I understand economic rationality as the following: outcomes are to some extent generated by agents deciding according to personal objectives. So this does not necessarily mean that agents are people. So agents can be the multiple selves of one person. It can be genes in evolutionary game theory and so on. Does not mean that people are intelligent or omniscient. Does not mean that outcomes on a macroscopic level appear particularly rational. Think of the prisoner's dilemma or of unstable financial markets. And the entire outcome need not be generated by agents' decision making. Okay, then choice, decision making is intrinsically linked to uncertainty, and the classical model of choice and uncertainty is the ACT, a map from states to consequences. So if you don't know in which restaurant you will end up tonight, well, then you devise for any circumstance one consequence. And the global idea is that given economically rational agents that interact in that way, this happens in strategic equilibrium. So what does this mean from a perspective of dynamics and probability? So the act actually can be directly reinterpreted in the dynamic setting as what we know under the name of a strategy, that is a complete contingent plan of action. For any state, again, we can select a consequence, and this can be represented in a particular way. So this is a remark made by Krebs, and it has been developed in a very specific but at the same time general setting by Alois Ferrer and Ritzberger in the 2000s and 2010s. Let me illustrate this using this figure. So suppose that, well, you will have a meal tonight in either an Italian or a Japanese restaurant, and you can choose to eat either pasta or fish. And these are the outcomes finally, the black dots. And when you're outside on the street, you can choose, still all options are possible. Yeah? So you are in the blue rectangle, and then you can choose one of these large red ellipses. Let's say you choose the lower one, the Japanese restaurant, say. So then you end up in the blue rectangle below. That's a state. And in this state, you can choose the small red ellipse on the left, on the right, so pasta or fish. Okay, that's a way of representing this based on a set of outcomes and on subsets of this set, partitions. And this can be equivalently represented using such a graph, a tree actually. And this is nothing else actually than the representation of dynamic decision problems, which goes back to von Neumann and Morgenstern from the 40s, and then Kuhn's extensive form theory using exactly this, trees. Yeah. And the already mentioned Alois Ferrer and Ritzberger have generalized this to a very large setting, which also covers formally continuous time problems in some sense. Okay. Well, what about probability? Rationality was also about personal objectives, and a typical way of representing this are relations on preferences. Are preference relations on on acts, for instance, and given a certain axiomatic model of rationality on these preference relations, this can be one-to-one represented using another classical concept from decision theory, that is expected utility. So you choose a strategy, or the agents choose a strategy profile, and this determines these probabilities here. And comparing strategies or strategy profiles is then equivalent to comparing the numerical values of this expected utility. Okay. So what is the core challenge of my program? That's complex dynamics and uncertainty. So if the tree from the slide before becomes a bit more complex, then we have two dimensions. We have the horizontal dimension, so the dimension of states. If that one becomes complex, then measurability becomes really a technical and also conceptual issue. So precisely, even if one is able to distinguish all states, not all sets of states need to be measurable. So we make some selection of sigma algebras as a modeler, but this is not completely objective. So in principle, the game's rules cannot depend on it. And along the vertical structure, along the dynamic dimension, if this becomes very complex, then the very notion of outcome generated by strategies easily becomes ill-defined. So it can become unclear what the outcome of a given strategic interaction actually is. And this is, of course, an elementary problem. Okay, that's the situation, and let's now tackle it. Let's continue with section 2, where I wish to argue why we need an abstract graded language of dynamic games and probability.
Hello, Emanuel. We have a question from Aditya. Can you pause
Sorry,
to take a question?
Yes, of course.
Sure. So can you go to the previous slide where you say that you don't want the rules of the game to depend on the sigma algebra? I mean, if could you elaborate on that? Because the way I see it, if I'm working in a probabilistic framework, I'll have to restrict my strategies to be measurable in order to talk about expected utility. And the moment I restrict myself to measurable strategies, I would have to commit to a sigma algebra at that stage. So
Yes.
what exactly why the rules of the game should not depend on the sigma algebra?
So in principle, one could perceive of different sigma algebras, and depending on the sigma algebra you choose, a larger or smaller class of beliefs is possible. And so the choice of a sigma algebra already restricts the set of beliefs which are admissible to an agent.
Yes.
So that's the point which I wanted to make.
So couldn't one view sigma algebra as a primitive of the game, that when I'm specifying the game, I need to specify the sigma algebra on which the underlying uncertainty would be defined at least, and then everything else could be a function of that?
Yes, one could do so, and this is also something which is done, for instance, in the product form approach by Witzenhausen and authors that use this. However, I do not choose to do so because I would like to consider the possibility that agents would like to strategically choose their sigma algebra. So, and would reason about the choice of the other players and so on.
Okay,
Yes.
all right, thanks.
Okay, thank you for the question. So let me continue with the second section then, where I give a bit more technical examples to begin with. So what do we wish to speak about? So first example, which is actually about what we just discussed following the question. I'd like to construct refined partitions or tree-based extensive form theory that incorporates the measurability of a map G from 0, 1 to the action space, describing a choice G of epsilon based on a signal epsilon that is uniformly distributed on 0, 1, and as 0, 1 is uncountable, this cannot be represented using partitions. So we have to make the measurability primitive in a certain sense, but I'd like to be as parsimonious as possible with this assumption. Then, second, I'm interested in determining the boundaries of an extensive form theory that is based on stochastic processes or equivalently paths of actions or random paths of action. And third, I would like to consider games that are beyond these boundaries, but which are very interesting for us, continuous time stochastic games. I would like to interpret the use of words like strategy, equilibrium, subgame, in terms of game-theoretic first principles. And of course, this applies to many important models used in finance, economics, and engineering, etc. This includes stochastic differential games defined in terms of stochastic differential equation of this form, where the system is described by a state process, and actually the equilibrium criterion is directly given in a strategic form of this kind, or also timing games where the state process is of this form for stopping time tau k for player k, and often one describes the payoff in this form: leader payoff, follower payoff, and simultaneous stopping payoff. Well, these are more concrete examples I'm interested in. And so let's return to the question why we need an abstract graded language of dynamic games. Well, first, let us recall that a non-cooperative game or decision problem is specified by a complete set of rules. And many of the notions that we use, like strategy, equilibrium, subgames, are derived concepts. So once we fix the rules and we plug in the data, the sets of strategy, equilibrium, and so on are determined. And this models the state of anarchy, that is the absence of rulers, as opposed to the state of anomie, which is the absence of rules. So this is not the same thing, of course. And the standard model that we learn in basic game theory classes is the extensive forms, which is based on decision trees or equivalently refined partitions, going back to von Neumann, Morgenstern, Kuhn, and having been generalized utterly by Allesferrer and Ritzbecker recently. So in order to address the mentioned challenges, this theory needs to be generalized and its limitations be characterized. However, we will find that there are objects sharing essential characteristics of these problems that cannot be formulated in extensive form, though. So the aim is to have, in the end, an intrinsic language of these characteristics, which I call extensive form characteristics, that also arise extrinsically as a limit of a strict stochastic extensive form theory. And here I define loosely extensive form characteristics as the flow of information about past choices and exogenous events, along with a set of adapted choices locally available to decision makers. So that's the primitive information that we build a model around. And once all the information of this nature is plugged in, the rest should follow. Okay. Then it becomes a bit clearer now what this outline means. There are two sections that remain to be discussed in this talk, 3 and 4. In 3, I will present the, let's say, rigorous and standard model based on forests and giving rise to an extensive form theory. And in the 4th section, we will go beyond extensive forms, and for sake of an illustration, I will focus on continuous time stochastic timing games. Okay. Then let us continue with section 3, which is about the model of extensive form characteristics using what I call stochastic decision forests. Okay, why stochastic decision forests, and why the notion of adapted choices that we then need based on these stochastic decision forests? Well, in the standard model that we learn in undergraduate classes, we only have one tree, and randomness, let's say exogenous randomness, so stochasticity, is typically modeled just by assuming an additional virtual player called nature playing some fixed mixed strategy. But unfortunately, this reaches its limitations relatively soon once one is interested in complex uncertainty and dynamics, because, well, first, a Brownian nature agent has no choice, because when you look at the choice of the Brownian agent at time t, contemplating past choices up to time t, but exclusively, given the continuity of the trajectory, the agent has to choose the left limit. So this is a bit paradoxical. This can be substantiated much further, and this has been done in the 80s and 90s by Simon and Stinchkamp, and then underpinned theoretically by Allosferrer and Ritzberger in the 2000s and 2010s. So this is really a structural problem. But second, we also have this measurability problem. If we do not wish to impose measurability conditions uniformly for the whole tree, then we get problems, at least in case we want to calculate interesting expected utilities in the end. So agents observing the value bt of the motion at time t can not really be denied choosing non-measurable functions f of bt of it, because it is not justified to exclude.
Emanuel, may I ask a question?
Yes, please.
By non-measurable, do you mean in the technical sense of a function which is not measurable with respect to, for instance, Lebesgue measure, or do you mean just not based on observations?
With respect to some fixed sigma algebra, let's say.
Okay, so for instance, the construction, I believe, of non-measurable functions requires the axiom of choice, brings in the axiom of choice. So does this mean that really one wants to consider agents that may want to invoke the axiom of choice in their decision procedures? It seems to be quite a restriction that one's going for a very ultimate form of generality if one actually fears that non-measurable functions might be selected.
Well, I think that from a really rigorous decision-theoretic point of view, it is not clear why one can impose on agents to choose, let's say, Lebesgue measurable functions. So, for instance, consider a game where, well, a leader chooses either 0 or 1, and then a follower chooses no, sorry, a leader chooses a number between 0 and 1, and the follower then gets informed about this and can choose A or B, let's say. And then why should we restrict the choice of the second agent to measurable functions from 0, 1 to the 2-point set? From a purely decision-theoretic point of view, it's not so clear. The reason that we want to do this is, well, we are mathematicians. We have learned Lebesgue measure theory, and we know that it's otherwise difficult to calculate an expected utility. But that's not really a decision-theoretic reason.
Thanks. Okay, thanks very much.
Sorry, can I ask a follow-up question? Just in terms of whether this is decision theoretic or not. So if I go one step further and say agents only have preferences over outcomes, then for Neumann and Morgenstern theory shows that if I have consistent preferences, that is equivalent to expected utility maximization. Yeah. And to have expectation, or I guess even to define preferences over outcomes on random lotteries, I need to have sigma algebra to talk about that. So how would you define a utility function and define rationality of agents if we are not specifying the sigma algebra and allowing agents to choose non-measurable functions?
Yes. Thank you for that question. I think it's absolutely important to think about this like that. Because in the end, of course, we need measurability. But the question, I think, is about the objectivity of the sigma algebra. So is this something that we impose on agents as a modeler, or is this something that agents can, to some extent, control? So can they, to some extent, control which sets they deem to be measurable?
And would such a choice be common knowledge to all agents before the game starts, or you are assuming this is private information to agents, their choice of sigma algebra?
I'd ask this question in general, independently of this.
Okay.
Actually, if I join in with a without delaying your timing, so quickly squeeze in an apology for derailing any timing. Actually, although this may seem debatable in a decision-theoretic framework, because we somehow always say, okay, we've got random variables here. Actually, from a physicist's point of view, it's actually more reasonable to question sigma algebras, because this is kind of a perennial philosophical question in physics. Is the universe really random? And then so you have to say, well, in what sense do you mean random? And so then one has to ask, well, is Brownian motion and Lebesgue measurability really actually intrinsic to fundamental particle behavior, for instance? And then these kind of questions become really substantive somehow in the decision theoretic, because it seems to be so human-based. One might say, well, look, we've got to assume random variables and get on with the job. But if one's discussing the intrinsic nature of nature, it's not so obvious. Yes. I've got a nod from Aditya, so we'll let you get on.
Yeah.
Get on with the job.
Yes, I agree. I think that when thinking about models for human behavior, the more tractable we want to make it, the more assumption we have to make. And finally, I remain in the framework of probability. So I assume that in the end, we will have agents that calculate probabilities. But the question is on what sigma algebra? And my argument is to say, and perhaps I advance one bullet point, is to say that, well, even if it's not so clear whether it is restrictive to fix sigma algebras at any stage of the game, so to speak, it seems reasonable to assume this for the root move. So somehow to outsource all the considerations of agents about the right measurability structure and about the beliefs of the agents about the measurability structures of the others and so on into the root move of the decision tree. So this is a mirroring of Harsanyian's argument in his papers on incomplete information games, where he outsources actually states and beliefs about states and so on into the root. And here I would propose to do the same thing with respect to the sigma algebras on the states. And this is what I would like to call exogenous uncertainty. And this is why I do not consider one tree, but several trees. So for any exogenous scenario, I consider a tree. And on the set of exogenous scenarios, or the set of trees equivalently, I fix one, and I would argue objective, sigma algebra that is perhaps very large, but which finally will contain everything. So instead of a dynamically acting nature agent, we have a static exogenous scenario space, a measurable space, omega E, plus a structure of dynamic updates, which are subsigma algebras of E and which tell the agents more or less in which tree they are, actually. So that's the idea of the first chapter, and then it is developed. So instead of one tree like this, we have a family of trees. So a forest with a decision structure, so a decision forest. And actually, this is quite compatible also with this passage from trees to forest. So a decision forest actually is nothing else than a forest of decision trees. Well, and then here in this forest, we identify, or we identify to a certain extent moves. So for instance, the roots are identified. It's these dotted lines. These moves are identified and these moves are identified in a certain sense. So actually we define sections, horizontal sections that identify these moves. And this serves as a device for exogenous information revelation. So to any of these dotted lines, which we can also see as maps from omega to the set of moves, so random moves. To any of these random moves, I attach a sigma algebra, a subsigma algebra of E, which tells the agent in which tree or in which gives the agent information about the realized tree, so to speak. And then, based on this, I can devise a theory of, or a notion of choices that is compatible with the refined partitions approach, the really classical discrete notion of choices along the tree dimension, but perfectly compatible with the idea of measurability along the horizontal omega dimension in the measure-theoretic sense. So on the horizontal axis, we have a full measure-theoretic generality. And this is a measure-theoretic generalization of the works by Harsanyi, but then in the extensive form setting by Alois Ferrer and Ritzberger from the 2000s and 2010s. I can elaborate on this further in case of questions.
Yeah, I'd actually ask you to do that since you are citing Witzenhausen. So in comparison with the intrinsic form, is the key difference that you are allowing the sigma algebra to be part of the uncertainty while it was pre-specified in the standard form, in the intrinsic model, I'm sorry.
Yes, I would say so. Yeah. Yeah.
Thank you.
And well, what comes in addition is, of course, that due to the extensive form structure, I have really a pre-specified notion of causality regarding decision-making of the personal players, which we don't need the qualifier personal anymore, but yeah, causality is built in, and outcome generation is built in to the model. Okay.
You're still allowing for non-sequentiality of moves. That is, along different sample paths, players can act in different order.
Sorry?
Are you allowing for non-sequentiality of moves, that along different sample paths, player can act in different order, which was a feature of the intrinsic model of Witzenhausen? Or is it assumed that the order in which agent acts is pre-specified and fixed along all sample paths?
Well, of course, for one fixed scenario, you always have this tree structure. So
yes, in Witzenhausen order, your information sets could be across time.
Yeah, what can happen is that, so to speak, these dotted lines cross.
Okay. Right. Yeah. Okay.
Exactly.
So, for instance, the absent-minded driver could be absent-minded driver story by Pichone and Rubinstein could be described like this. Okay. Thank you. Okay, I think I have to hurry up a bit. So let me just say a few words about the, properly speaking, extensive form theory based on this. So, of course, these are the ingredients that model these extensive form characteristics, as I call them, the basic data. But of course, we need some axioms to put this together in a consistent way and to call this extensive form, and I call it stochastic extensive form due to this extra stochastic component. And I formalize this in my work, and I also study the derived notions of, well, information sets, strategy, histories, and subgames. Yeah, we also get an intrinsic model of subgames, etc. And what is interesting, for example, is that information can be decomposed into one endogenous and into one exogenous component, as I call it. Yeah. Endogenous and exogenous, the words have many meanings in different contexts, but here I have already explained what I mean by exogenous, and endogenous is the component that describes information generated by agents through decision making. Yeah? And perhaps the most important point here in this table is well-posedness. An extensive form directly describes how outcomes are generated, but in case of complex dynamics, it's well known that this may actually fail So there may be multiple outcomes compatible with the strategy profile or none at all. And actually, one can characterize well-posedness in terms of the well-posedness of the scenario-wise extensor forms. And from this case, it is known from Alosfera and Ritzberger once again that simple order-theoretic properties of the forest alone characterize this well-posedness. So well-posedness does not depend on the choices, but only on the order-theoretic properties of the forest. And this implies two things. So first, complex dynamic exogenous noise like Brownian motion can be added without risking a loss of well-posedness. And second, if we consider this action path model, so stochastic processes, essentially, then we can show that well-posedness is essentially equivalent to the well-orderedness of time, which of course for continuous time friends is a problem. So then let's move on beyond the boundaries of extensor forms with an emphasis on the illustration of stochastic timing games. May I just ask how much time is left?
What do you think?
We can go
15 minutes?
Yes.
Yeah, 15 minutes is our estimate.
Okay.
We lose the room in, there's a hard stop in 35 minutes, a very hard stop. But certainly carry on for 15 minutes and then we can squeeze in some questions from around the planet because you've got a very international audience.
Yeah, great. Okay, thank you. Okay, then let me continue with the final section, which is about continuous time. Yeah, of course, not necessary to tell you that there are many, many important and interesting applications. So it's not necessary to explain why we want to do this, but well, why do we need to go beyond extensor forms in order to understand this? We have seen that there's a possibility theorem in case of well-ordered time. So stochastic extensor forms suffice for this case, but we have an impossibility theorem in case of continuous time, which confirms findings from the deterministic setting going back to Simon Stinchkamp, and Alosfera Ritzberger. So what shall we do? Well, I propose a weakly relaxed model of extensor form characteristics in continuous time. So extensor form characteristics, again, that's, let's say, the basic data of a dynamic game under probabilistic uncertainty. And I suggest to relax the following. Strategies are no more strictly derived from local choices, in the sense that there will be some regularity across time, which of course will imply that to some extent my choices today will depend on my choices tomorrow. This is to some extent a problem, but we will have to live with this. Yet we may be able to live with this because we can require certain local measurability conditions. Exogenous and endogenous information will still appear and will be jointly modeled this time via sigma algebras on configuration space time. So configuration space times time. And this, of course, is much more familiar given knowledge of the intrinsic form by Witzenhausen. But it is combined with ideas from stochastic analysis, going back to Langlar, the theory of Meillet sigma fields. I will go into more detail regarding this. But I would like to stress that otherwise the model is still based on outcomes. Strategies induce outcome processes, or strategy profiles induce outcome processes, and preferences are defined on outcome processes. So that is the excuse me. So that is the the step from moving from the dynamic description of the game to the finally strategic form equilibrium representation can really be factorized over outcome generation and preferences on outcomes. So we have a formal description of what happens dynamically, and this is important. And now I would like to explain this using the example of timing games. So here I consider a specific timing game in this illustration. So this is the value function scheme for a symmetric 4-player stochastic timing game in continuous time with an underlying one-dimensional diffusion, a Wright-Fisher diffusion living on the unit interval, and which in the long run converges to 1 and is absorbed in 1. So think of a game where four firms compete in a market 1, and they can decide to switch irreversibly to market 2 at some high fixed investment cost. The gains will depend on X, and in the long run, it becomes favorable to go in the other market, but still by oligopolistic reasons, it is always nice to be in a market with less competitors. So this creates a trade-off. And what is interesting here, so first, yeah, the solid lines are the value functions and the dashed lines are the boundaries. And stopping occurs when both meet. And here for the red player, the one who stops last, we have a smooth fit. For the green player who stops here, we have a smooth fit. For the blue player who stops here, we have the smooth fit, but for the purple player, we haven't. Here. This is not a smooth fit here. And the reason is preemption. If we made this player stop optimally, given his belief that the blue player stops here, the green here, and the red here, then the purple player would rather stop here. Something like this. But the blue player would have an interest to preempt the purple player, to stop 1 epsilon before the purple one. And so actually the purple player will already stop at the point where the blue player is indifferent about this. Okay, so this is more or less the logic, but although this is a very common model in economics and finance, also in continuous time for several reasons, it is really hard to describe this properly mathematically. How can we, how can we describe a theory of the symmetric equilibrium at the preemption boundary here? That's the problem. So in discrete time, players independently flip a coin to stop with higher and higher intensity from left to right, corresponding to the increasing first mover advantage. So the purple solid line is above the blue line, but the difference becomes smaller and smaller when we move to the left. In the unscaled continuous time limit, this logic collapses because then in the limit, both players will stop with probability 1 at the preemption boundary, but this is clearly not an equilibrium. So what happens with this equilibrium in continuous time? Does it exist? So there are several approaches to this. These include additional coordination mechanisms or sharing rules, or the extended mixed strategies for discrete time limit payoffs introduced by Fudenberg and Tirol in 1985 and generalized to the stochastic setting by Riedel and Steg in the mid-2010s. And the underlying logic is to extend continuous time strategies by a device that translates into timing strategies on finer and finer discrete approximating grids, and then to calculate the limits of the discrete time payoffs, not of the outcomes, but of the payoffs. So I would say that this is a discrete time approach to a continuous time problem. By contrast, I would like to propose a complementary view based on what I call vertically extended continuous time. And why do we need this? There are several disadvantages of the Fudenberg-Tirol formulation, I think. Despite its parsimonity in a certain sense. So we do not have an intrinsic continuous time model of outcomes. And the game is really formulated in stacked strategic form, and there's no clear way of providing a dynamic perspective on the problem on the level of outcomes. And this makes it also difficult to interpret the use of perfect or subgame perfect equilibrium. So rather than adding devices solely understandable in terms of discrete time approximations, I suggest to suitably extend the time axis in order to address the problem of instantaneous reaction and information about this. So ultimately, timing problems in continuous time require a notion of ordered simultaneity. These reactions, they collapse at the preemption boundary otherwise. And these problems, these timing problems, are arguably problems thus in vertically extended continuous time. So in these terms, I propose a vertically extended continuous time approach to what is a vertically extended continuous time problem. So I would like to illustrate this a bit. So as I said, a key issue is information loss regarding infinitesimal reaction. So let's consider for fixed n this grid, k, 2 to the power minus n. And let's consider Alice acting according to this action process, and Bob, which is xi n, and Bob acting with respect to xi n minus 1. So then Alice always goes to 0 or stops strictly before Bob. But in the limit, what happens? Well, they seem to stop at the same time, but at the same time, well, they don't really stop at time 0, but at any time epsilon greater than 0, they already have stopped. So it's a bit unclear. This is why I suggest to add, in addition to the horizontal time half-axis, R plus, a well-ordered vertical axis. Let's say the positive integers in this case. So we have times of the form 0, 0, 0, 1. And in this case, we can describe Alice's limit action process by this, the indicator of 0, 0, and Bob's by indicator of 0, 0, 0, 1. So they really stop in an ordered but simultaneous way. And this can be illustrated in this sense. If I have some third agent, Cassandra, who chooses actions A at this time, B at this really light gray dot, and C at this light gray dot on some grid Gn. And on grid Gn plus 1, she still chooses A here, but B at this gray dot and C already at this gray dot. And we continue like this with Gn plus 2 and so on. let n go to infinity, then ABC collapse at t. But with a vertically extended time axis, we can tilt all this onto the vertical axis. That's the idea. Okay. Okay, now I will hurry up a bit. In order to develop this on the level of stochastic processes, we really need a theory of stochastic processes on this extended time half-axis. And there are several non-trivial questions that arise. What is the right topology, the right sigma algebra? Do we have measurable section and projection theorem? What is a good theory of optional times, debut theorem, and so on? So there's quite some work to do, and this has been done, and it works. But for reasons of time, I'm not going to detail this here. So I think it's 2 minutes or something like this, which are left. So for that reason, let me skip the formal description. I apologize. And just, well, I will say one sentence for each slide. Okay, so we have now, based on the stochastic analysis, a model called stochastic process form of the game, which is based on the before mentioned extensive form characteristics. Okay. And in this model, we can describe the timing game and show well-posedness. Strategies are described partially by local measurability properties, and we can actually solve this stylized preemption game that I discussed before and reproduce the Fudenberg-Tirol and Riedel-Steg equilibrium using one strategy process. And we can describe the outcome process induced by this strategy profile explicitly as a stochastic process, which moreover arises as a tilting limit of the discrete time outcome processes from the well-known discrete time equilibrium. Very rough description of what happens. There are some subtle differences actually to the model by Fudenberg and Tirol. Even in the conclusion, but already on the formal level, there's an important difference. So we have one strategy process because the dynamic perspective arises really on the level of outcome processes. We have derived counterfactuals. This is also a difference. And we have an intrinsic model of timing outcomes. So as I said, a vertically extended continuous time model for a vertically extended continuous time problem. And I'm happy to develop a bit more on the equilibrium at the preemption boundary, because this is particularly interesting point here. So with this, let me conclude that I propose in this work an abstract graded language for game theory that addresses the interplay of complex uncertainty and dynamics. The core notion describing the corresponding data are extensive form characteristics. There's a strict reading of this, which is based on decision trees, which together with the specific concept, Harsanyian-like concept of exogenous information, gives the notion of stochastic decision forests. These in turn, combined with classical concept of choice under uncertainty yield the notion of adapted choices. Based on this, we can describe a theory of extensive forms and characterize well-posedness. In an action path-based model, this well-posedness is equivalent to time being well-ordered. And in continuous time, we can set up a relaxed intrinsic model called the stochastic process form based on a stochastic analysis in vertically extended continuous time. And this can also be extrinsically motivated by tilting convergence out of well-posed stochastic extensive forms. This opens a new perspective on various problems, for instance, on preemption, and more generally on stochastic differential games. If you're interested in more information, you find a list of references in my doctoral dissertation and much more explanations, of course. And I'm also happy about any question by email. And thank you for your attention. And I'm looking forward to the discussion and your comments.